In this video, we are going to be going over section 3.3, graphs of polynomial functions. So first we have some properties of polynomial functions. So the domain of all polynomial functions is going to be all real numbers. In other words, the interval from minus infinity to infinity. And the range of odd polynomial functions is going to be all real numbers. And we could realize this again by just thinking of any linear function with non-zero well-defined slope. While the range of even polynomial functions is going to be restricted by its minimum or maximum. So in the case that the leading coefficient of an even degree polynomial function is positive, then the range is going to be, well, whatever that minimum value is for the even degree polynomial function to infinity. And in the case of a even degree polynomial function with a negative leading coefficient, the range is going to be from minus infinity to whatever its maximum value is. And again, here we can think about the graphs of parabolas. Okay, so that's domain and range for polynomial functions. The other thing that we are going to be interested in this section is identifying the zeros of polynomial functions and their multiplicity. So for a polynomial function, what we want to do is set the function equal to 0 and factor the polynomial function. And then once we have the polynomial function factored and set equal to 0, then by the principle of zero products, whenever either of the factors is equal to 0, well, the product of all the factors is going to be 0, and so the function's value is going to be 0. So the zeros of the polynomial correspond to when any of its linear factors are equal to 0, once we have it in factored form. And we will define the number of times a given factor appears in the factored form for our polynomial functions as the zero's multiplicity. So some examples of some polynomial functions in factored form. We have f of x equals x plus 3 times x plus 2 times x minus 1. So this is going to be a degree 3 polynomial function. And it has zeros of -3, -2, and +1, and each of these zeros has a multiplicity of 1. Okay. Another example would be g of x equals x minus 2 squared, or in other words, g of x equals x minus 2 times x minus 2. So this polynomial function is a degree 2 polynomial function, of course, and it has 1 0 at x equals a +2, and the multiplicity there is going to be 2. So a polynomial function's behavior near its zeros, like looking at its graph, is given by the multiplicity of that 0. So the graph of a polynomial function will touch the x-axis at zeros with an even multiplicity, and it will cross the x-axis for zeros with an odd multiplicity. So in either case, since the function's value is going to be 0, the graph will be intersecting the x-axis. The only difference is that in the case of a 0 with even multiplicity, it won't actually, cross over to the other side of the x-axis. It's just going to intersect and then bounce back in the other direction. Whereas if we have a 0 of odd multiplicity, we will see the graph of our polynomial function, intersect the x-axis at that 0, but then it'll cross to the other side of the x-axis. So with that in mind, for our first example, we are going to state the multiplicity, assuming the lowest multiplicity for any of the zeros that we can see. So we are going to either assume the multiplicity is going to be 1 or 2 of each 0 for the following graph. All right, so let's go ahead and identify its zeros. So we have a 0 over here at the point -2, 0. A 0 here at the origin, 0, 0, and then a 0 over here at 2, 0. And so from the graph, well, according to what we just said, at the 0, x equals -2, since the graph of our polynomial function, it crosses the x-axis there. So just to the left of this 0, we're above the x-axis, and just to the right of this 0, we're below the x-axis, so it crossed the x-axis there. And so since we're assuming the lowest multiplicity, this means, well, since it crosses, the multiplicity is odd, and since we're assuming the lowest, we're going to assume it's 1. So we'll say 0 of multiplicity 1 at x equals -2. Okay, and then continuing on, so for the other 0 at the origin, 0, 0, again, if we look at the graph, so just to the left of the origin, the graph is below the x-axis, and just to the right of the origin, the graph is above the x-axis. So here, the graph is crossing the x-axis at that 0, so we would again assume the multiplicity is going to be odd, and since we're assuming the least, we're going to say 0 of multiplicity 1 at x equals 0. Okay, and then continuing to our other 0. So for the 0 at x equals 2, well, the graph just touches the x-axis at x equals 2, but it doesn't cross it. So it intersects the x-axis, but it doesn't cross over to the other side. So to both the left and to the right of x equals 2, our graph is above the x-axis. So that means we have a 0 of even multiplicity there, and since we're assuming the lowest, we're going to assume it's 2. So 0 of multiplicity 2 at x equals 2. All right, in the next example, we're asked to use the following information about a polynomial function to determine a formula for that function. So we're told that it's going to be a degree 5 polynomial function with a y-intercept at the point 0, 9. So we'll be able to use this point to find the value of our leading coefficient a. And then it has roots of multiplicity 2 at x equals 3 and x equals 1, and a root of multiplicity 1 at x equals -3. So again, a 0 at x equals 3 is going to correspond to a factor of x minus 3. So let's go ahead and write f of x, and then we'll put a out in front, and then we'll start writing our first factor. So since we have a 0 at x equals 3, we're going to have a factor of x minus 3. And since the multiplicity there is 2, we're going to have 2 factors of x minus 3. So in other words, x minus 3 squared. And similarly, since we have a root of multiplicity 2 at x equals 1, well, having a root or a 0 at x equals 1 corresponds to our polynomial having a factor of x minus 1. And since the multiplicity is 2, we're going to have x minus 1 squared. All right, and then we have a root of multiplicity 1 at x equals -3. So a root or 0 at x equals -3 is going to correspond to a factor of x plus 3, or x minus a minus 3, which is the same as x plus 3. And since the multiplicity is 1 there, we're just going to have one factor of x plus 3. All right, so this is what the formula should look like. And indeed, this is going to be a degree 5 polynomial function. So the way that we can check the degree of a polynomial function in factored form is just by adding up the multiplicity of each factor. So we have a factor of multiplicity 2, another factor of multiplicity 2, and then a factor of multiplicity 1. So the degree is 2 plus 1, which is going to be 5. So we don't have to worry about there being any other factors here. We have all our factors, and this gives us the correct degree of 5 for our polynomial function f. So the only thing we have remaining to find is our value for a. And so once again, we are going to say, okay, well, we're told that f of 0 is equal to 9, again, because f has a y-intercept at 0, 9. And so that means when we plug in 0 for x, the function's value is going to be 9. So we have 9 equals a, and then times 0 minus 3 squared, times 0 minus 1 squared, times 0 plus 3. And let's simplify what we have on the right. So we're going to have 9 equals a, and then 0 minus 3 is just going to be minus 3. And then when we square it, we're going to have a positive 9. And then 0 minus 1 is going to be minus 1 squared is going to be a positive 1. And then we have 0 plus 3 is just going to be 3. So we have 9 equals a times 9 times 1 times 3. In other words, 9 equals 27a when we multiply everything out. And so solving for a, we divide both sides by 27. And we get that a is equal to 9 over 27, which reduces to 1/3. So now we have the value for our leading coefficient, so we can go ahead and write the formula for f. F of x is going to equal 1/3 times x minus 3 squared times x minus 1 squared times x plus 3. And yeah, we aren't going to worry about multiplying things out here because that would just be a headache. And yeah, you don't have to worry about multiplying out your answers in Lumen either. So if you're asked to come up with a polynomial function based on some information, probably the first equation you are going to be able to come up with for your polynomial function is going to be in factored form like we have here. And yeah, once you have that, you don't have to worry about multiplying the factors back out. Again, you might be worried about doing that just to check the degree, but like I said, we can always recover the degree by just adding up the multiplicities. All right, in our next example, we're asked to use the graph to write the formula of a polynomial function of least degree. So let's go ahead and identify its zeros. So we have a 0 here at -2, 0. And then at 1, 0, and again at 3, 0. So since it's saying that it wants us to write a formula of the polynomial function of least degree corresponding to this graph, well, we kind of like that first example we looked at involving the multiplicities, we are going to assume that the multiplicities here for the zeros are going to be 1 or 2. And let's go ahead and check and see what the multiplicities are. So for the 0 at -2, well, since the graph crosses the x-axis at x equals -2, that means that this 0 has an odd multiplicity, and since we're going to assume the least, we're going to say its multiplicity is going to be 1. Similarly with the 0 at x equals 1. So again, the graph crosses the x-axis. So once again, we're going to assume that its multiplicity is 1. And then for the 0 at x equals 3, we again have the graph crossing the x-axis. So we're again gonna say that the multiplicity at x equals 3 is 1. All right, and then we are also going to want to know the y-intercept because we are going to use that to recover the value for the leading coefficient like we did in the previous example. So this point here is going to be the point 0, 3. Okay, and so putting all of our ingredients together, so since we have a 0 of multiplicity, so let's go ahead and write f of x, then equals, and then a, our leading coefficient. We're going to have to figure that out. And then for our first factor, well, for the 0 at -2, that is going to correspond to us having a factor of x plus 2. And since we said the multiplicity is 1, we just have one factor of x plus 2. And then for the 0 at x equals 1, that's going to correspond to us having a factor of x minus 1. And again, since we said the multiplicity is 1 there, we just have one factor of x minus 1. And then lastly, for our 0 at x equals 3, that's going to correspond to our polynomial having a factor of x minus 3. And again, we said the degree was 1 there, so we're just going to have one of those factors. All right. So this is what our polynomial function should look like up to figuring out the value of that leading coefficient a. So let's go ahead and do that now. So since the y-intercept is at 0, 3, this means to us that f of 0 is going to be equal to 3. So we can use that to say, okay, 3 equals a, and then times 0 plus 2, times 0 minus 1, times 0 minus 3. So 3 is equal to a times 2 times minus 1 times minus 3, which is going to give us, so we have double minuses, so a positive 3 times 2 is 6, so we have 3 equals 6a. And so a is going to be equal to 3 over 6, or 1/2. So now we can go ahead and say f of x is equal to 1/2 times x plus 2 times x minus 1 times x minus 3. Okay. In the next example, we are asked to sketch the graph of the given function and identify its degree. And so in the first of these, well, in our one example of this kind of problem, we are given the polynomial function in factored form, f of x equals x squared times x plus 4 times 2x minus 5. So for the degree, again, we can just add the multiplicities. So if we add the multiplicities, we have a 0 of multiplicity 2 at x equals 0. So since we have the factor x squared, this means we have 0 of abbreviate multiplicity 2 at x equals 0. And then since we have the factor x plus 4, this means we have a 0 of multiplicity 1 at x equals -4, and then 2x minus 5 equals 0. Well, if we set 2x minus 5 equal to 0 and solve for x, we're going to get x equals 5 over 2, or 2.5. So we have a 0 of multiplicity 1, again, because we only have one factor of 2x minus 5. At x equals 5 halves, or 2.5 if you prefer decimal. So let's go ahead and plot our zeros. So here's our point, -4 comma 0, and 0 comma 0, the origin, and then 2.5 comma 0 is about right there. All right. And then, so let's go ahead and figure out the degree. So we can add up the multiplicities. 2 plus 1 plus 1 is 4, so that the degree is going to be 4. Again, we don't have to worry about multiplying this out, but if we wanted to, we would find that the term of highest degree is going to be, well, 2 times x to the 4. So the degree is 4, so it's an even degree polynomial function with a positive leading coefficient. So that means to us, so let's say even degree and positive leading coefficient. I'm just going to abbreviate LC. This all tells us that f of x is going to go to infinity as x goes to plus or minus infinity. So we could go ahead and draw our end behavior arrows too. So just to the left of our leftmost zero here, we could do one end behavior arrow that's just kind of pointing up and to the left. And then to the right of our rightmost zero at x equals 2.5, we will do another end behavior arrow, just pointing up and to the right. Okay, and since we have a 0 of multiplicity 1 at x equals -4, that means that the graph is just going to cross the x-axis there. And then we're going to want to go back up to our other 0. At the origin, and since the multiplicity is 2 there, we're just going to want to go up to the origin and touch the x-axis, but not cross it. Okay. Since we didn't cross, we have to go back down and then up to our other 0 at x equals 2.5. And since that is another 0 of multiplicity 1, we're going to be able to cross the x-axis there and connect with our other end behavior arrow. And yeah, so we don't have to worry about, let's see. So the y-intercept here, by the way, since we have an x-intercept at the origin, that's also going to be our y-intercept, so we don't have to worry about, plotting that point in this particular case. So that's our graph. All right. So In the case that we don't know exactly where one of the zeros of our polynomial function is, or just any function in general that is a continuous function at least, which polynomial functions are, we have this little theorem called the intermediate value theorem, which can kind of help us locate the zeros, or at least get a general idea of where they are. So if we let f be a polynomial function, and if we have that f of a and f of b have opposite signs, so if like f of a is positive and f of b is negative, or vice versa, then there exists at least one value c between a and b such that f of c is equal to 0. So we are going to use the intermediate value theorem to show that the polynomial p of x, which is going to be equal to x cubed plus x squared plus x minus 1, has zeros in the interval from 0 to 1. So here 0 is going to be our a, and 1 is going to be our b. And what we want to see here is that f of 0 has the opposite sign of f of b. And if we have that, then, we want to see that p of 0 has the opposite sign of p of 1. And if we do have that, then we can use the intermediate value theorem to conclude that p of x has a 0 in between 0 and 1, or in the interval 0, 1. So let's evaluate p of 0. This is just going to be 0 cubed plus 0 squared plus 0 minus 1, which is of course going to be equal to minus 1. And then p of 1 is going to be equal to 1 cubed plus 1 squared plus 1 minus 1. So this is going to be equal to 1 plus 1 plus 1 is 3, and then minus 1 is 2. So we have that p of 0 is negative while p of 1 is positive. And so since p of 0 is less than 0 and p of 1 is greater than 0, meaning they have opposite signs, p of x has zeros in the interval 0, 1 by the intermediate value theorem. So even if we do not know these zeros of a function, if we find the output values change between two input values, then we know there is at least one 0 between those two input values.